think my insurance is paid up, so we're all good. What did I make? Okay, here we go. Welcome back, guys. Today is gonna be fun because I need to build something to break this brand new Fireball Hardtail Vise. So when I set out to design this vise, I wanted it to be the strongest vise possible in its weight class. Everybody knows if you use a vise properly, it should never break and it should last a lifetime. But that's really not what happens. When a vise gets abused, things break. Like the swivel base likes to break, they're a typical weak point. The jaws like to snap off. This whole assembly will just literally just fall off. This chin right here in the bottom, this is notoriously known for cracking and splitting off. The jaws right here in the bottom will split. Dynamic jaw slide, the castings like to split apart right there. But these are all problems that I don't know if I solved when designing this vise. I knew that I wanted it to be the strongest vise you can buy. So I took inspiration from old vices and new and started testing them. Along the way, I developed my own torture test, something to identify the weaknesses in the vice's construction. One of my torture tests includes hitting a bar clamped into a vise with a hammer. Although not very scientific, this does get me the forces needed to break the vise. The first thing I'm looking for is the swivel base to snap off due to the high impact force. Also, how strong are the jaws? Are they able to hold on to the bar? Also, can the screw handle this type of high impact loads? As much as I like this test, there's one fatal flaw. Fatality. Me, the human. There's just no way for me to swing the hammer at a consistent force every single time, and at the correct angle. This is a real problem for scientific results. I know what you're thinking. You're saying, Jason, why would anybody put something in a vise and hit it with a hammer? That's not what a vise is designed to do. So why are you even testing that? So I'd like to use the example of a car. Cars are designed to drive, get you from A to B. But at some point in time, they might crash, so they need to be tested in this scenario. I'd also like to randomly crash test a Fireball Hardtail Vise as they come off the production line. This is going to ensure that these vices are up to my satisfaction, and yours. That way you know you can abuse them and they're going to last for a lifetime. So I want to build a machine that's going to pound on these vices for me over and over and over again so that I don't have to. So let's talk about some ideas on how to make this vice hammering machine. The first idea that I have is that we can use compressed air from an air compressor to move a cylinder. I like this idea because it's going to operate much like a blacksmith's power hammer. I also don't like that it's going to be very complex with all its moving parts, valves, switches. I'd like to keep this machine simple, so maybe a mechanical hammer is the way to go. Maybe we just add a motor, hook it up to a spinning flywheel, and then a spring to deliver the 1-2 punch. I like this idea, but I think it's going to be limited by its range of punching motion, and its ability to vary the force applied. But I think there's one more option. We can use gravity. We can build a rig really high in the air, get a weight up there at the top, and then drop it, landing on the vise. Because the motion is linear, it's going to be a little tricky to elevate the weight back up to the top again for another hit. As much as I like all those designs, I think I want to kind of keep traditional. What I'd like to do is replicate the swing of a human as closely as possible. And when you look at a human swinging a hammer, he swings it in an arc. Not only have I never seen a machine do this before, which adds an extra element of difficulty, but I think it's just going to look plain cool also. This is the hammer that I used last time on those little tiny 20, 30 pound vices. This vise weighs 270 pounds. So we need to increase the hammer size. This big, long, tall swing is gonna move that head approximately 6 or 5 feet throughout a radius. This is gonna be one crazy looking machine. So I think this hammer is a little too small for this rig. And I have an idea of something I'd like to replace this hammerhead with. Something that's gonna work perfect for this. This is the last place I saw it. When I first thought of this machine, this is the thing that came to mind. Oh, look at that in all its rusty glory. This is a drill bit used for well drilling. I bought it for the material because it's tool steel. Do I need it for anything else? No. But when I saw it, I just had to have it. If there's one thing that's going to destroy this vise, it's going to be this. I'm curious to see what these hammers weigh. So the first one that I was using just for fun was 4 pounds, 1 ounce. This one with the steel handle, 13 pounds, 7 ounces. 53 pounds, 10 ounces. I'm starting to question my decision with this hammer. but I think it's gonna do the job. So now that I've chosen my hammerhead, it's now time to figure out how I'm gonna attach a handle to it. This hammer is gonna be seeing a lot of vibration and abuse. The easy solution is just to weld a piece of tube steel directly to the hammerhead. But welding mild steel to tool steel can be tricky sometimes. And I'm a little bit nervous that that weld is gonna snap off at exactly the wrong time. So I'm gonna play it safe and design a clamp to hold on to the hammerhead. This also allows me to have a mild steel to mild steel weld joint. This also allows us to change out the hammerhead to anything we want later on. Because who knows, maybe this hammerhead is too big or too small. Or we might need something special. This hammer is gonna have a 3-foot long handle to simulate a normal sledge. We also need to add a pivot to the end of the handle so that we can have it swing. So the hammer has a spline section. So I'm going to be using the water jet to cut a ring to grip onto it. I'm cutting it out of 3-inch mild steel plate. The overall weight of this thing with the handle is going to be right around 77 pounds. This thing's going to be heavy duty. Oh, dunk, look at that. All right, now the handle. This is a piece of solid bar stock, and it's going to be the axle. This piece of pipe goes over this axle. When I section this piece off, we're gonna need to weld what I'm gonna call the handle, and then this to this. So let's chop all these things to the correct dimensions, and then we can start welding it all together. All right, here's the challenge. I gotta get this to all line up. So this is 3 inches thick. This is 2 inches thick. That means I need a 1/2 inch elevation to get this tube into the center, and I'm going to use these magnetic blocks. So now what I have to worry about is where is this? So let's set ourselves up some stops. If this is the first time you've ever seen a fixture table like this, these things are so cool. Because of these holes, this is a grid, and it allows me to adjust all of these stops, which are called fixtures, and set up cool parameters to be able to build and make some constraints. And I want to be 3 inches from the center line of this tube to the face of this block. So this needs to be 2.5 inches from this face to this face. This stop will reference on this flat spot that the water jet cut. Now when this comes into here, that's centered. This one, I just want it to be touching the groove. I love being able to fit it all together first before you make any welding. That is just so convenient. So let's weld it up, put some heavy beads on there, and we'll move on to the next part. So I got this thing all welded up, but if I had 20 of these arms to do, this would be really simple to drop all my components in, set up the clamps, and go to town and start welding. But in this case, perfection is what I'm after, and that's what I got. This is the action. Swing that hammer. Now we need to talk about how we're actually going to swing the hammer. So here's the problem. We have 2 ways to swing it. So the first motion is a swinging arc. Once the hammer comes to a complete stop, it can then return on the same path that it came, making a back and forth motion. To me, this is a very unnatural, mechanical motion. The second way to swing the hammer is to make a continuous circle, which means once the hammerhead strikes the object, it slightly continues along that same path, making a continuous loop. This has a much more natural, organic motion to it, and I think it's much more doable and something we can replicate with a motor. First, we have a few more problems we need to solve. We know we're going to add a motor to this thing to swing it, and we have one pivot point. Once the hammer makes 1 revolution and hits the vise, the hammerhead comes to a complete stop. This is bad because the motor could burn up in this instance. We need to find a way to keep the motor turning and the hammer going in a complete circle, even though there's an obstruction in the way. So I think the idea is we add another pivot point. This allows the motor to make a continuous revolution and at the same time picking the hammer up off of the vise, giving us the clearance we need. I think that'll solve one problem, but now we have another. We need to figure out a way for the motor to pick the hammerhead up too and return it to the top of the stroke. I think we can do this by extending our pivot arm and adding a permanent stop that grips onto the handle of the hammer, and gravity takes over and it repeats the cycle all over again. At least this is what I think should happen. Hopefully, but there's only one way to find out and we need to build it. I'm going to be making these pivot arms out of 1/2-inch plate steel. These things need to be extremely strong and durable. But the other problem is they need to be perfectly aligned with each other. Or also, the bearings aren't going to be aligned and it's not going to spin very free. To ensure everything is going to be perfect, I'm using the fixture table again. Aligning all the parts is pretty simple. but holding it in place as you weld it and keeping the distortion out, oh, that's a whole nother problem. A lot of you can relate from something warped during welding and it doesn't fit, then having to cut it apart and trying again. But having the proper tools like this table makes things like this easy. And once I had the hammer and the swing arm assembly all put together, it was now time to start thinking about the frame. This is going to be the structural backbone of this hammer. Its job is to hold the hammer swing assembly off the ground. So I'd like to keep this frame simple, then we can attach the swing arm to the box. One more criteria is that we need to be able to analyze the hammer striking the vise. So I need to remove anything that's going to be obstructing our view. The frame also has to be able to accommodate different heights of vices. One way we can do this is just change the handle length. But that's going to be bad because that's going to change the force that the hammer is applied to the vise. So we're going to need to raise and lower the entire swing arm assembly. We don't want the hammer hitting the vise itself, only the test bar. And we can do this by just adding a slip joint tube. The frame also needs to be able to accommodate two different hammer attack angles. One is the horizontal attack and two, the vertical attack. We can do this by simply rotating the frame around 90 degrees. This is going to lower the height of the swing arm by several feet, which is going to be quite nice. So let's get started with building the frame. I'm going to be using 4x4 square tubing, but there is one side to this box that's a little tricky. One side actually has a 70.3 degree angle on it, which is kind of unusual. Typically you'd use a protractor to set the angle up, but I have an easier way, is just use the grid pattern of the welding table. Much like an XY measurement or coordinate system, I can go up and over to a certain distance on each one of my fixtures, setting the perfect 70.3 degree angle. And now when I go to weld this all out, I can pull the frame out and insert all the same tubing, and it's gonna plop right in the same spot, and then I weld that out and I will have two identical frames when I'm done. So the frames turned out pretty cool. It's a lot bigger than it looks on CAD. Now I just have to figure out how I'm gonna get that hammer attached to these tubes. Let me take you over here and show you the plan. First thing we're gonna need to do is build basically a motor, gearbox, and bearing assembly. This is what's gonna provide all the pivoting and moving action. So the motor I wanna use is this little 110 geared reduced electric motor, and it turns 60 RPMs in 1 minute. And these things are really cheap. You can find them on Amazon for like 130 bucks. And I'm only using it because it's what I had laying around. The bearings I want to use are from a trailer. Trailer bearings and axles are pretty tough. They're designed to take a lot of pounding and they're pretty easy to work with. And you can buy all the individual components to build an axle. And in my case, I'm only going to be using the outer section of the axle. I'm going to be taking that stub axle shaft, welding it to a base plate along with the motor mount. Basically what I'm going to be doing is replacing where the wheel went and exchanging that for my swing arm. And my motor will turn the swing arm much like it would have done the wheel. I'm going to be cutting the motor mount out of some heavy duty 1/2-inch plate and making sure to add some slots into the motor mount. That way we can do some fine adjustments a little bit later. So I need to make sure that this is welded nice and square and perpendicular to this plate, and we'll be able to get this sucker mounted and we'll go on to the next step. So now that that project's done, it's now time to get this axle shaft mounted to this base plate also. So I got my fixture set up. It's kind of rinky-dink, but let me show you what I got. I have to have this axle and this plate welded together, and they have to match. What I got is a riser block. This is gonna get welded down because I need a little extra elevation. So it goes up against this block, and these blocks. To set the depth where it goes, I'm gonna bump it into this fixture right here. And then I'm gonna clamp it down, and then I'm gonna weld this axle to this block and this block to this plate. Put the hub on, a couple bearings. Now, this is looking kind of cool. Now that we have a motor and a way to spin the hammer, now we have to really think about how fast is this hammer gonna spin. I don't want the hammer to spin too fast because it's gonna self-destruct. We also might not have enough torque to lift up this really heavy hammer. The motor is already gear reduced, but at 60 RPM, that's already too fast. So we're gonna have to add some gearing. I really don't wanna use gears because that locks me into a specific gear ratio. I could use some pulleys and a V-belt, but man, V-belts just like to slip sometimes, especially when going slow. So I think the best thing to use is some chain and sprockets. I think this is gonna give me the versatility that I need without making any compromises. This whole motor mount assembly cannot be attached to the frame. It needs to be attached to the moving arm so that when it elevates, this whole assembly moves with it. I'm going to be attaching the chain to where the wheel used to mount. This way the swing arm is going to spin just like the wheel used to. So I need some sprockets. I'm going to use the water jet to make them. Flow has provided us with the software to make any size sprocket we want by simply using its Flow Cut program. I'm going to be cutting the sprocket out of a material called Strengths 700. This should be adequate for my project. The water jet can cut me a sprocket within 1/1000th of an inch, which virtually means I need no machining on this. And in about 8 minutes time, I have myself a sprocket.
Look at that, that's beautiful.
The Strength 700 is a little bit too thick to fit inside the roller chain, so I took it to the lathe just to thin it out just a little bit. So I have sprocket and spacer.
And then we replace the studs with bolts. Look at that. Okay, now the motor goes on like that. It all fits.
The next problem we have is that the shaft on the motor is metric. Finding a metric sprocket for 40 chain is quite tricky. I even went to the tractor supply store to find one, but no luck. So the simplest solution is just to make my own. I like this option because I get to choose the number of teeth. And once again, if I need to change it, I can.
Here she be, nice custom sprocket. Let's see if it fits. Perfect fit. So a lot of people are afraid to use chain because they don't know how to cut it, but it's actually pretty simple. Here we have this main link bar and we want to remove it. We're going to have to grind this peened over pin and we're going to push it out with this tool right here. Ta-da! And to get it to go back together again, we use this. This is called a master link and this is a replaceable link, which means when you need to remove or install the chain, you can just pop this side clip out like that. Boom! The very last thing we need to do is getting these axles welded to the end of these tubes. It's alive! Look at that funky thing. So far it's lining up not too bad. That's like pretty straight. I'm happy with this so far. So I got the whole thing assembled. So what I like to try to do is just see it do a thing without the motor. So let's put this rag box underneath here and watch what happens. This is technically right after the impact. Gravity has taken over, the hammer has hit whatever we put underneath here. Now the motor is just gonna continue to turn and it's gonna start lifting. That's the only job of this motor, is to lift until this arm, boom, makes contact. And then all of a sudden, we're reloaded, ready to go. The hammer's at the top of the stroke. And then once it tips over top dead center here, oh yeah! I know that seems quite uneventful, but believe me, that would probably hit pretty hard. It's like sweet in simplicity. It's like so simple and elegant. And to have this thing do it over and over and over again, I think we're ready to proceed to get the motor wired up and we can try some cycles. Power's on. That's the right way. Oops. This motor doesn't have the torque. Stopped it. Nope. It doesn't have the poop. We don't even have the weight on the end of it yet. So this first test was a major disappointment, but I kind of expected this. And I actually like having problems because it gets my brain thinking. So the couple options that we have to choose from is one, we can choose a bigger motor. Like I said earlier, I've had this one here in the shop, so I just wanted to use it because I already own it. Don't have to buy anything else. So the second thing we can do is increase the gear ratio and give this little motor a little bit better opportunity to turn this hammer. The third option is to figure out some way to take the load off the motor, and we can do that by adding a counterweight. I know I could sit here and probably figure it out, some moving weights, some other swinging arms, that would probably all work. But in all reality, I think what we really need to do is just increase the gear ratio. So let's take this whole thing apart. Let's lop off the motor and let's add some more gears into the sucker and get this thing the mechanical advantage that it needs. So here's the current configuration. Small sprocket, large sprocket. Since my large sprocket is already spinning slower, I can use that to be the next drive sprocket. So all I need to do is attach the smaller sprocket to the large one. And then all I need is another large sprocket attached to the small sprocket. Again, this is going to significantly increase the torque of that little motor.
To keep things in a nice neat package, I'm just going to fold everything over onto itself, making it fit in a much smaller area. With that being said, it's time to cut some more sprockets. Because I need as much torque as possible, I'm making the sprockets even bigger than the last ones I made. More teeth, more power. I had to make a little stub shaft with some bearings in it to hold this idle sprocket. I also had to make a whole new motor mount that got welded to the existing one. Which is no big deal. It's just one of those things you have to deal with when you're inventing a new machine. When I first started welding, fabricating, machining, I had somebody tell me once, what's the difference between a good mechanic and a bad mechanic? And he said, the good mechanic knows how to hide his mistakes. And I've always thought of that when stuff happens like this.
Let's see how smooth it is. Some mechanical advantage there. That's a good sign. The gearbox resistance was holding it up. So I'm really happy the way this turned out. I love the gearing, and I think that's the best thing to think about is how do you cover up your mistakes to not make it look like a mistake. All right, let's do another test run. Here we go, here we go. Yes, it's lifting. Okay, touch. Yes! Look at all that torque. Swing, baby, swing. Woo! Whoa! Yikes. Ah! Yeah! That was quite violent. That's why we shouldn't be dry firing it. Let's put a box under there. Nice and slow. Nothing stops it. Not a little box. It definitely needs something to hit. Let's see what happens when we add another 53 pounds. Okay, moment of truth, little motor. Okay, going good. Oh yeah, yeah. Okay, I'm gonna stop it. I'll be honest, I'm a little scared. I guess there's only one way to find out what's gonna happen. Okay. So let's get this thing bolted to a secure base and let's put something underneath here and crash something. So got this thing all set up. It's tack welded to the table. So before we actually try putting the vices underneath here, I think we should try something a little bit easier just to make sure this thing stays together. So I say we should try a cinder block. This should be no problem, but I'm kind of curious to see how it acts and reacts to the swinging motion. I put this tube back here just to keep the cinder block from just kicking out. This should just destroy the cinder block. I have the high-speed camera set up, got some lights, I got my safety glasses. I'm gonna be standing way back in the back. So enough talking, let's get to it, huh? All I gotta do is plug this thing in, and then I'm gonna yank the plug out after it makes contact. Okay, here we go. 3, 2, 1, go. Okay, seeing liftoff. It's lifting great. I mean, that's exactly what I want to see it. They go high, clear the object. Okay, we got contact. Have it going really slow on purpose just to make sure everything's going good. Oh crap, here it goes. Oh! Oh! Oh my gosh, woohoo, look at that. That was totally successful. Wow. This thing has a lot of power. That block was like it was not even there. That was a pretty successful test, but I want to try something else. So let's crush a mega square. This is going to simulate dropping it and see what happens. All right, let's do this. 3, 2, 1. Here we go. Oh my goodness. Oh. My heart's beating out of my chest. I don't know why. The anxiety's killing me. Okay, here we go. 90 more degrees. 3, 2, 1. Here it goes. Oh! Holy crap. That's one tough square. Everybody says that cast iron's weak, but if it's designed properly, look at that. Let's see the high speed. Ooh. Man, that square's 30 pounds. That thing flew. It needs round 2. Let's do it again. Glasses on. Hide behind the go-kart grinder here. 90 more degrees. Okay, here it comes. 3, 2, 1. There it goes. Oh! Oh my gosh. Crazy. Oh, we gotta check out the high speed on that one. Let's see what it looks like. Here it comes. Boom, crack. Plays pinball in between itself. Wow, and it just sends it flying. Man, look how it squirted that bar out the bottom. So there was a GoPro attached to this. Apparently, if I was right in line, yep, here it is. Oh, dang it, it broke the lens. That's okay. This is gonna look cool.
So for the first test on the hammer rig, let's test out this unbreakable K-Tool 8-inch vise.
One of these things is not like the other. So here's some things to consider. This thing looks pretty weak around the base. 3 bolts and a piece of mild steel flat bar held on by a 1/4 of an inch grip there. The base is only 3/16 of an inch thick. Might break off from the feet. This might pull through. This might break. That bar might bend. The connection between the jaw and the base right here where it's welded, it's definitely probably gonna bend. Or we literally snap the screw off. But one thing's for sure, I guarantee I'm gonna break it. Even though it says unbreakable steel construction.
So this hammer rig is designed to hit this test bar. And I'm gonna put the test bar right here on the outside edge of the jaws. Optimum would be the center. Off to the side is gonna put the jaws in twist, and it's gonna put a lot of force on the swivel base, because I also wanna see how well that holds. Every test I'm gonna ever do is gonna be performed off center. So I'm just gonna clamp this as hard as I can, and then we're ready to go. Predictions, I think it's gonna take 4 hits for something to break. First thing that's gonna break is the swivel base, that flat bar that goes across the bottom. That's just gonna fold in half and the vise is gonna go pew and flying off the table. 4 hits, that's my guess. Here it goes. Oh, sheesh. That's scary. Well, that didn't take very long. Why can't anybody make a good swivel base? This is the weak spot on every vise. Did I not predict that that bar on the bottom was going to fail?
Yep, I knew that was gonna be a thing. Bent it.
That's what this rig is designed for, to find the weak spot.
Bent the bolts.
Let's just put it back together, hit it one more time, and send this vise flying. Hit number 2.
Oh man, that's scary.
Yeah.
Lifetime warranty, unbreakable.
Let's check out the high speed. Oh, that's pretty cool looking. So I'm really happy with the way the rig turned out. Obviously, it does some serious destruction to whatever goes underneath of it, and I look forward to putting the vices that this was designed for underneath this machine to seeing how they hold up. But that's going to be part 2, so I'll see you guys in that video, and thanks for watching.